Hello students, welcome back. We just talked about confidence intervals. Very, very important computation. Now let's talk about confidence bounds. Maybe not as important as confidence intervals, but almost equally as useful. Confidence bound is similar to confidence interval, except that we are looking for only one side. Here's a visualization of confidence intervals. From here to there, centered at the best point estimate, symmetrically, because we have normal picture which is symmetric. Now let's look at unbounded confidence interval, starting from 1 and then going forever, or starting from here going the other way forever. These kind of numbers are called the confidence bound. This one, lower confidence bound, and this one is upper confidence bound. In this case, we get unbounded confidence interval, and mu1 to infinity like this, or negative infinity to mu2 like this. But we rarely call these confidence intervals or unbounded confidence interval. We simply say confidence bound, 95% confidence bound, 95% lower confidence bound, 95% upper confidence bound, or let me change it into 8%. Now 98% lower confidence bound, 98% upper confidence bound, like this. Now, here's a warning. Let's go back to the default. Here's warning. This number is called the lower confidence bound, or in this case, 95% lower confidence bound. This thing is called the lower bound of 95% confidence interval. This one here is the upper bound of 95% confidence interval, while this one is 95% upper confidence bound. Oh boy, it's confusing. The lower confidence bound and the lower bound of a confidence interval are different. Same goes for upper. I'm terribly sorry, but these terms were invented far before I was born. If I had any say on this, then I would not have developed such confusing terms. But it's too late. Historically, people developed all these in separate means, and now it's too late to change anything. So be careful about those. I'll try not to scrutinize these too much, but if the occasion arises, I will take some points off. Not too much though, but 1 or 2 points out of total 10. Yes, I will, because they are different concepts, and confidence bound concepts are important as well. Alright, so much for theory, and let's do some example problem here. And remember this problem? A certain college selected a random sample of 100 commuting students and obtained the students' one-way commute distance. The resulting sample mean was 10.22 miles. Estimate mean one-way commute distance of all commuting students of the college using the standard deviation of 6.0 miles. And let's consider 95% upper confidence bound. We already did 95% confidence interval and got the upper bound and lower bound. 95% upper confidence bound. So we have confidence bound only to the right, nothing to the left. And we subdivide by 95% and 5%. Not 95%, 2.5, 2.5. You see? This one goes on forever and 5%. Comparatively speaking, 95% confidence interval looks like this. 95% in the middle, so the other 5% is shared here, 2.5, 2.5. Not like that, because this is lower confidence bound problem. Oh, excuse me, upper confidence bound problem. Alright, we have this picture, and how do you solve it? Well, z-score is end minus center over SE. Oops, what did I do? I don't know what I clicked. Let's get out and restart. Don't worry, I can get back pretty quickly. So we were here, confidence intervals, and we were doing upper confidence bound problem here. Okay, and then z-score is end minus center over SE. And in this case, or this one, upper confidence bound, U minus center is 10.22. And then what is standard error? Sigma over square root of n. So 6.0 standard deviation over square root of 100. And this should be approximation. Nothing is accurate in statistics. So whenever you have numbers, this should be approximation. And now this has to be associated to the shading of 95%. And if you look up the normal table and find out the z-score associated to this 95% shading, you're going to get 1.645. Let's go there, 95%, so it should be in the second page. And look up something closest to 95%. So you have 0.9495 and 0.9505. Those are push. So here 1.64, 1.65. So we take somewhere in the middle, 1.645, and that's the estimation you have. So solving this equation, you have U is approximately equal to 10.22 plus 1.645, the z-score, times SE. And if you punch in the calculator, you're going to get something, 11.20 something. That's going to be the 95% upper confidence bound. Let's do it again. Now let's look for, oh, by the way, the solution is here. 99% lower confidence bound. Okay, visualization is like this. Now we have lower bound, and this is 99%, which means I have only 1% here. All right. Okay, lower confidence bound. And what is my z-score? Z is n minus center over SE. And it is lower bound L minus center 10.22 over SE, which is sigma over square root of n, 6.0 over square root of 100. And that's approximately equal to the z-score associated to this 1% here. If you look up the standard table, the shading of this left is 1%, and look up the z-score associated to that 1%, you're going to get negative 2.33, approximately speaking. Let's go there. Let's see. Less than 50%, so the first page. And where is 1%? This is the closest, 0.0099. And that corresponds to negative 2.33. Negative 2.30 and 3 column here, negative 2.33. Make sense? So this is negative 2.33, And solving this equation, you're going to get this. L is approximately equal to 10.22 minus 2.33 times standard error. And punch in the calculator, you're going to get something. So from here, subtract the margin of error, z minus SE, and that z-score, as you looked up, was 2.33. And I'm going to the left because this is negative. Okay, so much for the visualizations and everything for upper and lower confidence bound. And we previously discussed confidence intervals, and those are both important examples. Confidence intervals are a little bit more important than confidence bounds, but they're both important. Now we have more examples on confidence intervals, and this one is about determining the sample size. Let's see. Suppose that the weight of boys in a certain school district is normally distributed with a standard deviation of about 3.0 pounds. Determine the sample size in order to estimate the mean weight within 1 pound with 95% confidence. Looks like there are too many unknowns, but don't panic. Yes, you can do it. Okay, here we go. We have a normal picture. And then the center, I don't know. And I'm not completely sure either. And then we have 95% confidence interval, right? So 95% in the middle. And by the symmetry, we're going to have 5% shared left and right symmetrically. So here we have 2.5%. And then another 2.5% here. Now, what else do we have here? So best point estimate is this value, and this distance here to the center to the end point is going to be the error bound within 1 pound. So from here, plus or minus 1 pound. So here we have x bar. Here I have x bar plus the margin of error of z times SE. And here I have x bar minus z times SE. So see, end minus center over SE is z. So end minus center okay, all right, here. So end minus center is this minus center. So we just get z minus SE. Z times SE. The margin of error is 1.0. And then z-score is associated to 95% confidence. So you can look up and find out. 2.5% there to the left. So look up and z-score will turn out to be negative 1.96. If you take this one, positive 1.96. And then SE is gonna be sigma over square root of n. So 3.0 over square root of n. So 1.96 sigma 3.0 over square root of n, and that's 1.0. We have an equation, one unknown, n value. Yes, you can solve it. Okay, I ended up spending a lot of time because of lousy drawing. Okay, here's a better picture. So end minus center is Z is end minus center over SE. Come on. So end minus center is Z times SE. And you see, we want the error bound. So this is the margin of error, end minus center, either this way or that way. And that's going to be Z times SE. And that has to be, in this case, approximately 1.0. %, so 1.96 times SE, which is sigma over square root of n. And that's approximately equal to 1.0. Yeah, from this equation, you can solve for n. Here's a solution. So 1.0 is n minus center, and eventually 1.96 times 3.0 over square root of n. You can solve for square root of n algebraically. And then taking square, we get 34.57. Now, here's a tricky deal. We have to have an integer, right? And we have to round up because this is the error bound. This is error bound, so we do not want to exceed this. So how do you reduce a little bit of your standard error? By increasing n value a little bit, because that goes to the denominator. That's why we have to raise always up. Round always up. So 34.26 still rounded up to 35. That can be a bit tricky. Here 34.57, so no problem. Round up to 35. But even when 34.167 still rounded up to 35. So that can be a little bit tricky. I guess that's it. Is there anything more to discuss? The theory of interval estimation? Oh boy, this is different. And this is something I'll have to discuss in an optional video. So let's not worry about that. I'll say we just completed section 4.